Recording. All right, we're recording.
The broadcast is now starting. All attendees are in listen-only mode.
Okay, I think everything is good to go. Good morning, everyone, all 17 of you. My name's Adrian Jensen. I work for Predictive Engineering, and I've also got George Laird on the line here.
Good morning.
And his audio is working as well. We're going to do a little FEMAP and Nastran technical seminar on Groundcheck because last month we were at a symposium and somebody mentioned Groundcheck and that you should do it, and after about 1 second then they went on and we were like, hey, what is Groundcheck? We need to dig into this. And it's something we've always seen on the Analysis Manager, and said, one day we're going to actually figure out what that is. So we put some time in and built some example models to investigate that. First thing I want to bring up here is the help files, because the first thing we do when we go into one of these new topics is dig into the help. There's going to be tons of information there. I've got Nastran or FEMAP open here. This is one of my example models for later. If you haven't used the NX Nastran help, it's a little bit different than the FEMAP help. Help topics, Control H, will go to the FEMAP help library. And that's a lot of the information on the modeling side of things within FEMAP. But if you want to get into a little more in-depth analysis information, help NX Nastran. Now, my default browser is Chrome, and I don't believe it works in Chrome, so I'll switch over. We'll try Firefox here, and I'm just going to copy and paste this URL in here. You can always set up your default browser to Firefox or whatever you want. What I've done, though, is, so I don't have to go through the browser each time, is I've actually downloaded the PDFs, and I have them on my desktop for quick access. Oh, thanks, George. A few other things before we get started is if you guys have questions and you haven't done one of these with us before, the GoToWebinar application has a little chat box. It has questions, so you can punch in your questions. If we don't get to them during the webinar, we can follow up afterwards. And if you see us having problems with audio or you can't hear us, be sure to put something in the chat or the questions and let us know, and we'll fiddle around with our plugs here. Okay, so the NX Nastran help, we're currently on 8.5.1, and you see this pop up here. We get a quick reference guide, a release guide, and an error list. But if you go back to 8.5, and Firefox is trying to prevent me from opening Windows, why I download these. If you go back to 8.5, you see that you get the full library of NX Nastran help. And the ones that I use most commonly are the quick reference guide. It's a little less bulky and has kind of a broad range of material, and the user's guide, which has a little more in depth. So you can download these PDFs for quick access, or if you just want to access them through the browser like this, you now know the steps. I've got these downloaded here. Let's start with the quick reference guide, and we'll just track down Groundcheck. There we go. So the Groundcheck performs grounding check analysis on the stiffness matrix to expose unintentional constraints by moving the model rigidly. George and I were talking about this morning, and where this really comes from is Nastran's rich heritage in aerospace and vibration. When you've got this plane up in the sky and you need to perform some vibration, it's not fixed to ground. It's not a cantilever beam rigidly attached to the wall. We want these kind of floating, free vibration checks. And so when we perform this ground check, when we see the word pass, we know that we're truly ungrounded, a truly free analysis. But that's not to say that we can't use ground check on models that are going to be constrained for a static stress analysis. And I'll start out with that, and later on in the webinar we'll move to a free vibration analysis.
Yeah, that's what I would say.
Okay.
It's I want to also jump in a little bit and add in that if you're doing any sort of aviation work, spacecraft, anything that floats in space, the free sounds obvious. You just don't put any constraints on. You expect to get the body to vibrate perfectly. But if the matrix is ill-conditioned and there's things that just, elements get twisted and connections go bad, it's quite sophisticated what goes on inside the stiffness matrix and correspondingly the mass matrix, because you need both for an eigenvalue analysis. So the care and feeding of these matrices is not always obvious, and so that's why they have the weight check and the ground check, so that you can be assured that everything is clean and functioning, so that when you get your normal modes out and your frequencies, that you can be assured that at least that part is working well. Okay. Good.
That's good. Thank you. Here's the NX Nastran user's guide that I've pulled up, and it's got a little bit more descriptive verbiage about the different things that will be checked with a ground check. And the most important piece of information that I've pulled from this was this little table of the DOF, the degree of freedom sets, and a description of when those sets are checked with ground check. We'll get even more information in the FO6 file to figure out how to debug some of these things. So I've got a little PowerPoint presentation here that we can put online once we post the webinar. And I've snagged that table out of there, and also snagged a screenshot of the page in the Analysis Manager where you activate these corresponding ground check DOF sets. One more introduction, and I'll get to some modeling here. Strain energy. One of the main things that's important to understand with the ground check is strain energy. And I think in some of our other vibration webinars we've introduced this for a given mode shape. It's the amount of elastic energy stored in an element. So if we have a free structure and we're getting, we should expect some rigid body motion, our strain energy should be very low. It's just translating or rotating as a rigid body. So when we start to see high strain energy, that's a red flag that something is grounded. This is just more goodies from the NX Nastran User's Guide, a little more in-depth information about strain energy. All right, let's pull up some actual models here. I'm going to start with this tower. It's one of the FEMAP example models. We like to use them because they look good and they're already built. This one's I've changed up a little bit. We've got the tower, some mass elements. The tower is modeled with beams. Turn on our thickness here. I've got a rigid link, an RBE2 down at the bottom, which is fixed at the center. That's if we're going to do maybe some seismic analysis later on, that can be our independent node to drive things. And then to simulate maybe some sort of flexible attachment, I've used CE-LAS elements here, and I've got them aligned in the X, Y, and Z direction here, so we can adjust the stiffness of this connection. In my Analysis Manager, I'm going to go through, walk through. I think you click Next maybe 6 times, and you get on the model check page. And by default, these are all turned off, and you get no ground check. We're going to turn these on here, and we're going to analyze the model, and we're going to look at the different degree of freedom sets, what passes, what fails, and why. I've already got a constraint set you can see here. So, okay, quick little model. I'm going to open up the Analysis Monitor. I just double-click that to make it a little bit larger, and we'll go to the FO6. I'm going to work my way up, and I start to see these pass, fail, these little tables here. And this is what the ground check generates in your FO6 file. So this first one, this is the G set. I can bring this back up for reference, the G set. So this is before single point constraints, before multi-point constraints, and before rigid elements are applied. So there's really no sort of constraint equations, no nodal constraints, and no rigid bodies in the model yet. This is just our elements. For our model, it's just our mass, our beam, and our spring elements.
Yeah, hey Adrian,
Mm-hmm.
go just a second, go back to your PowerPoint. Because I want to mention that it's, you know how you say and rigid elements,
Mm-hmm.
the G set and rigid elements? Because rigid elements are, this is what we covered under connections a couple months ago, that rigid elements are not elements, they're multi-point constraints. They're just set up, they have, for ease of use, they have these RBE2 and RBE3 nomenclature within Nastran, but they're really set up to be constraints. Is that you have an independent set and dependent set, and it's all being manipulated as a constraint within the stiffness matrix. So that's why they rip them out in this first pass.
Yeah, it's a good thing to bring that up too, because in this documentation they say multi-point constraints and rigid elements when really the two are one and the same. But in my next model, I've got both, and they result in the same sort of background mathematical setup. But we'll kind of talk about how you would set up, or how you would create a multi-point constraint or a rigid body element differently as far as just managing your model. But in reality, like George says, they're not elements. You're not getting strain energy in your rigid body.
Yeah, they're the same. I guess if I were to rewrite this, I'd say multi-point constraints, and I put a parenthesis and rigid elements close parenthesis.
Yeah.
And not differentiate because they're the same. So, okay, moving on.
All right. So at this point, before we've applied any of those, we're getting some failures here. They give us some information on why we might be failing. And actually, here's the uppermost. Once you see failures in your one of your ground checks, you will continue to see that failure in all subsequent ground checks. So it's best to start at the top, start at the G set here, and work your way down. The FO6 file is nice. It gives us some information on why we might be having some problems here. We know it's nothing to do with our constraint or our rigid elements. And most of them here are dealing with CELAS elements. So you could have a CELAS connecting to only one grid point, non-coincident points, or non-collinear. All of ours are connected to multiple grid points. We've got one end on the beam, one end on the rigid link. We're not using coincident nodes, but I tried to align them to their respective degrees of freedom. If you look around this model, though, I've got this kind of side view, and this one's all slightly skewed. Now, of course, I did this on purpose so we would get some failure and get something to debug, but this is something to look for is, all right, do I have any skewed CELAS? There's three different solutions for this problem. Is one, we could move our nodes here. I'm going to move these nodes, and I'm just going to move them up one so they're back into alignment here. You can see from the side view now they're nicely aligned. So that's one. Now they're collinear with their degree of freedom. The next one is to move both nodes of the spring to the same location and have coincident nodes. And the third option is to avoid using CELAS altogether, switch to C-Bush, and you don't have to worry about this problem so much. But different industries have different analysis requirements. You might be requested to use CELAS by your client. So here's a couple of ways to fix them if you are having problems. So let's run this again. Here's my FO6. Scroll back up, we'll find that uppermost ground check. Now everything's passing. My strain energies are down. Now that those CELAS elements are aligned with the correct degree of freedom, everything is happy. We get down to the next set after multi-point constraints / rigid bodies. Everything is still passing. We work our way down. Next is the auto SPC, which I'll talk about a little bit more in the next example. Still passing. And then finally we get failures at the F set. And if we go back to here, the F set is after single point constraints. So our nodal constraint down at the base there has been applied, our model is fixed, we're grounded, and we show a failure. For this case, a failure is not a bad thing. And actually, if you read some of the information here in this last set, the model is not intended to be free-free, which indicates that the model is properly constrained to ground. So for a static analysis like this, a failure at a certain point in your ground check tells you that your model is constrained. So that's okay. Okay, I'm going to wrap up with this model and move on to the next one, which is actually a free vibration. So once we're done with this, we want to be passing all ground checks. I've got a couple of different housings here, some rigid elements, and a beam element down the center for my transmission shaft. And this is a full model here. I just have my clipping plane turned on to help kind of illustrate the guts of what's going on here. To turn off thickness, you can see I've got some connections between the different housings, some constraints on this end. I wanted to simulate this being attached to a rigid engine block, so I fixed that there. And let's work our way through. And some of you guys might already be identifying problems with this model, but let's do it step by step and take a look at the F06 with each one. Now this time I'm going to be running a normal modes analysis, but you still get the options for ground check. Working through here, ground check, and I've got all these turned on. So let's analyze. Okay, first one way up here. Where is it? First one is the G set. We're getting some passes and some failures. Again, this is our CE-LAS elements. If you look at the way that I connected these two flanges with CE-LAS elements, I got from the outer ring there to the inner ring, they're not collinear. And with this sort of case, I can't get all my X, Y, and Z collinear, and I can't have my nodes coincident because I actually have a little gap between these two flanges. So what I want to do here is I'm just going to get rid of them, and I'm going to use C-bush elements. Delete these real quick by property, and I have, let me make sure all this is undeformed. There we go. So I'm going to delete mesh by property, and I've got 3 properties in here for the X, Y, and Z degrees of freedom. All right, we'll get rid of those. And now I'm going to connect these two with C-bush elements instead. This is a little bonus here, is this meshing trick, because it's really useful when you have to kind of zip things together like this. Mesh, connect, closest link. What this allows you to do is go from one group of nodes, select node to generate from. I'm going to use the on-curve method, and I'm going to pick the edges of this flange here. There we go. Then we pick a node to generate to using the same method on curve. And I want to generate to the nodes around the edge of this flange. Okay, so I've got my from group, my to group. Now I can pick what sort of connections I want to make. I'm going to make a new property, a new line element property. And this time we're going to skip the CE-LAS. We're going to go straight to a C-bush or spring damper element. We'll put in some values here. There we go. Now a C-bush is a little more complex than the CE-LAS. It works kind of like a beam element. We're going to need an orientation vector here. Since our C-bush elements are going to be running along the z-axis, I just need to pick a orientation vector that's perpendicular to that. And there they are. All right, let's run it again, see if we've eliminated our first problem. G set. All right, everything's passing. All right, the next set we have failures. This is after multi-point constraints and rigid elements. I've got some multi-point constraints connecting these two. I wasn't worried about modeling in some sort of spring to simulate the stiffness of the joint. I just used these little multi-point constraints using that same connect closest link command. Some of them are having problems though, and I can go ahead and delete these and replace them, but to find out exactly which ones are having problems, we can use the strain energy output of our normal modes analysis to help us highlight some problem areas. So I'm going to go to the post-processing toolbox. I want a contour, and the contour I want is strain energy. There you go. So you can see in our first mode we're getting high strain energy at these locations here. And if we deform the model, we're getting some really weird bending here. And what I've done, again, to give ourselves a good example, is I've gone through and intentionally botched some of the constraint equations. So rather than moving in unison like these two, these are actually moving in opposite directions. And we've had some models before where the constraint equations weren't properly input, and it was a serious chase to figure out what was going on, because it's not a commonly used connection method. Most people go with the normal rigid element or a C-bush, but we've seen these before, and it was really tough to chase down.
Yeah, and I want to say it's sort of embarrassing that's before we understood Groundcheck and what it was for. And so we were chasing our tails, and if we would have known this about the Groundcheck, we would have immediately gone here, looked at it, and said, oh, look at this. Instead, it was a couple days. But so people say, we do these technical seminars, and yeah, a big part of it, we do it for ourselves. It's a great training exercise. Okay, back to you, Adrian.
Alrighty, so the constraint equations here sit within the constraint set, and they're down here buried under equations. You can see there's a ton of them. So to hunt through and find the ones that would be problematic one by one would take a while. We can edit this and, oh look, +1, +1. If you know anything about constraint equations, you got lucky and found the first one was the problem child. In this case, we're just going to get rid of them, and we can rebuild them just like we built those C-bush. It'll be a little revisit to closest link for you guys, because I really like this tool. I use it a lot, and so it's not a bad thing to work in here. One side is our from group. The other side is our to group. Down here. Okay, and this time we're going to pick constraint equations. And I want my x, y, and z, so it's going to be like a little pinned connection at each one of those nodes. And there they are. Let's see if this fixed our problems. All right, there's our G set. There's our N set after our constraint equations. So we're passing in all but the 4 and 5 directions. So we've gotten a change here. Before they were all failing. Now we're only having 2 failures. And I guess I kind of almost stumbled upon this. I wanted to know what would happen if I would have less problems if my nodes were coincident for my constraint equations. So let's do that. I'm going to pull this together. I'm just going to move these nodes. Move to node. I'm going to move all those guys so they're coincident with their neighbors. I already mentioned that I wasn't as concerned with this joint, hence using the constraint equations. So closing up our gap there wasn't quite as much of a problem. All right, back up to the end set, and now everything's passing. Okay, stay awake. We only got a few more to debug here. The next set was the F set, and so this is after single point constraints have been added. Now I told you guys that I wanted to simulate a big rigid engine block on the end of this thing, so I fixed it. That might have been a red flag right away, because not only was I creating a rigid face here, I was constraining that face from translation. So a better way to simulate this rigid face, or this face being mounted to a rigid body, would be to get rid of this nodal constraint here. I'm going to delete this, and I'm just going to replace that with a rigid element. That way it's free to translate, but it's still a rigid face. I'll go model element. You guys get a little bit of modeling in here to make it a little more exciting. I'll do a new node at the center and grab the nodes on these outside curves. Alright, so I've got my rigid face. You can see we're chewing through them. G set passing, N set passing, F set passing, and the A set is passing. So we've really got through everything here. I think I may have missed one thing that I wanted to set up on my test model, and that was permanent constraints. Yeah, I may have ended up the model without it. This was another sneaky one that's sometimes hard to identify, and since my model didn't have it before, I'll go ahead and add it right here. Say you have a wide range of constraint sets that you're going to be working with, but you're always going to have one thing that's fixed, and you don't want to apply that fixed constraint in each of your constraint sets. You can always make a permanent constraint. And they're a little sneaky. Modify, permanent constraint. So I'm going to permanently constrain this node here. So this node on the end of the shaft is going to be fixed in all translational and rotational degrees of freedom, regardless of which constraint set I'm using in my analysis. The problem with these permanent constraints is by default, they're not drawn or labeled. You can delete all of your constraint sets and they're still there. So this is one where it's an older technique to use these permanent constraints, but you're gonna run into it, and using Groundcheck might be a good way to identify them. So with this permanent constraint here, we're going to go back and we're going to see some sort of failure. There we go. So in the F set, after we've applied constraints, you see failure. So the Groundcheck can be a really good way in rooting out some of these more sneaky constraint equations, sneaky permanent constraints, and other sort of modeling techniques that you might not be super familiar with. George, what do you think? Is that kind of beat the dead horse there? Is there any other examples that we need to cover?
It's one of those things. We can go on this stuff. One of the things, go back to the Analysis Manager on the Groundcheck page. One of the things we try to do is not to make these seminars too long or that technical. It's technical enough out there. Right there. The concept is give you a bit of exposure, show you how we figured this out, going through the documentation, building small models, having that two together, documentation, building stupid, simple, small models to debug stuff, it's the best learning you can find. What we didn't talk about was the weight check on this page. And this goes back to when you're doing an eigenvalue analysis, and this is to address, somebody asked a question, is there a specific type of analysis that we really use the model check on? And eigenvalue is normal modes is what I would think is the most common. This is what would jump out at me. And the weight check, you're looking at the mass matrix. So when you do a normal modes analysis, it's an eigenvalue equation. You're solving mass times acceleration plus stiffness times displacement equals 0 because it's normal modes, unforced. It's like taking a hammer and whacking on something and it vibrating. So you have two matrices that you're having to condition. You have your mass matrix and your stiffness matrix. Both can have problems inside of them. Both can be ill-formed, ill-conditioned. They both can have difficulties within them. So what the weight check does is allow you to perform some of the same checks that you would on the DOF. And as you can see, the nomenclature is the same, except for the very last, they give you an extra one, V, which is for component mode synthesis, and it looks at something, the residual, which is, well, more than I know. If I ever have to dig into it, I'll let you know. So that's my comment. And what Adrian has been showing here is how you would address it for a static analysis under Groundcheck. And of course, it's applicable too to normal modes because of the stiffness. So, okay, that's my comment.
I guess some of the things that weren't covered quite in depth here is one was auto SPC, when you have really small stiffness terms, which I didn't have in either of my models, but you have something very small and flexible next to something very rigid. You would see these small stiffness terms, and you can have an option to zero those out. So that was just one more step along the process. Add in rigid links, add in multi-point constraints, add in SPCs. There's also adding in auto SPCs, and within the help documentation it says if you see a failure at this stage of the ground check, it's an indicator that Nastran has automatically over-constrained your model with auto SPC. Some of the other options here, data rec, data recording. You can print your forces or strain energies in the FO6 file. I guess that's another way to track down your problem areas. I was using the contour, kind of the visual approach on screen. Reference node. I believe in some of the debugging tips they give you after each ground check, if you think you've got everything set up correctly and you're still getting some failures, it mentions that maybe the user specifies the reference node and makes sure that it's close to the CG of the model. And then finally is max strain energy. By default, Nastran has a strain energy value that it'll use as a pass-fail criteria for ground check. In the NX Nastran guide, I think it says it's 1% of the largest stiffness term, or I'd have to go back and look. But if you're an advanced enough user and you're using this a lot, you can go in and set your own strain energy levels here. Okay, we've got one little fluffy API to throw in here at the end, wake you guys all up. If you know me, I dink around with the APIs a lot, and we're also very graphically oriented here. So I'm going to go ahead, pull up my programming API window here, and we're going to hold on 1 second. All right, so I've got this GFX Vector Arrow API, and it's really simple. This is the whole code here, and I basically came up with this program. It was a spin-off of another API that I'd seen, and it's just for graphics. Sometimes you need to point at something in your model and your load vector is not visible, or you need to highlight something, and this creates a GFX arrow. And this is a graphic thing that you can only get to through the API as far as I know, so it's pretty useful. You click Run. It wants to ask you if you erase all previous. We'll say sure, and then you just pick 2 points to make a vector here. And there we've got a vector. It's kind of a nice shiny 3D vector. You can put them at different points through their model. The longer they are, the size scales with them. If you guys need different colors here, I kind of highlighted this section and gave some example colors. We can change the code. You can actually do some programming yourself. So I'm going to use my color equal to 4. That'll give me a red arrow. And delete this. And punch in some red arrows here. You can also punch in your coordinates by hand. So this was useful in some of my engineering reports. I need to say, all right, here is our problem area. Instead of drawing in some squiggly arrow in MS Paint, I have this nice 3D arrow here. And I kind of wanted to say thanks to a different Adrian Pavgao, I believe his name was, that showed me this GFX Arrow command in the programming. So this.
Hey Adrian,
yeah.
Before you got, did they know about the GFX measure tool that's out there for making measurements on your model?
Yeah, I think that was in maybe not our last webinar, but 2 webinars back.
You have that tied in to somewhere simple. You can show them that that's there too.
Yeah, so I've actually incorporated that one into my toolbar here.
You don't have the millimeter one. Okay.
So this one here uses a different style. Yeah, a different style of GFX Arrow, but it's a little more complex code. But yeah, I believe 2 webinars ago we incorporated that one and uploaded it with our webinar.
Okay. Yeah, we should do them both, and you can change the text styling, size, and format.
Yeah, because the arrow's the GFX arrow object, and then this text is just a normal text box that you could go in and modify.
Oh, so you can change the color of the arrow within that box?
The arrow is the GFX, so you have to do that.
Yeah, that's what I thought.
But then you can change this within.
Okay. I wanted to mention that for our support clients under Applied CAX, I know Adrian goes through this pretty fast. He's had years of using the program. You can see we use different colors and settings, and we do a lot of customization of the interface, and it's to make it look a little bit flashier, and modeling tricks. So if you guys would like a seminar with us and just spend half an hour on the web and have us tune up your interface and show you some tips and tricks, please send us an email. It's not a big deal. We're glad to help out. So all you got to do is let us know, and we'll schedule it up. Okay, that's my comment. Adrian?
I think that covers it. We're good to go.
Good. And this will be posted on our website. It's all video, so it has to get packed up, and files get big, and we've got to throw the seminar in, the GPX, so we're going to have it onto our website in a few days. And when we get it all set up, we'll send in an email to the attendees saying it's live. So that's it. Have a good day. Adrian.
Excellent. Thanks, everyone.